So our equation for starting is, we're going to say m dot c dt dm, all right, this is, sorry, dt m, the mean fluid temperature, dm dx. Try that again. M dot c dt m dx is equal to heat transfer coefficient hx times perimeter times ts minus tm. All right, so this would just come from doing the control volume analysis with a specified surface temperature. Okay, so if we start from this point, what we're going to do is just kind of walk through this and solve this ODE. Right? This is an ODE in terms of TM. So first step would be, let's kind of rearrange things, write it in standard form. So we have dt m dx plus hx perimeter over m dot c times tm is equal to hx perimeter over m dot c times ts. Okay? So again, remember here, tm is the thing that we're solving for. Ts is constant. So this is our familiar looking ODE. It's a non-homogeneous first order linear ODE. Right? First order because it's the first derivative is involved. So we can solve this. We just have to do that, that homogeneous particular solution, or that substitution. So we can do that. We'd say Tm is equal to T, let's call it Th plus Tp. We're making that substitution. We can write out the homogeneous part of the equation. So this is dt h dx plus hx perimeter over m dot c times th equals 0. So just a reminder on this. This homogeneous equation is all the stuff that's multiplying our independent variable, t sub h, equal to 0. Right? That's the definition of the homogeneous part. We can solve this. If you go to a table and look for the solution to this, it is th is equal to exponential of minus hx perimeter over m dot c times x times some unknown constant c1. Okay, so first of all, I keep saying hx. I just want to be clear. It's not h times x, it's h at position x. Right, so it's a local heat transfer coefficient. That's point 1. Point 2 is, if you look at this now, we can sort of see the behavior we're going to expect. Right, this is giving us a clue about how this solution is going to behave. And it's going to behave like a negative exponential. As x gets bigger and bigger, the value th gets smaller and smaller. So we're going from like some effect at the beginning that's noticeable to that sort of tapering off at the end. That's what we're going to expect to see. We'll worry about that C1 later. So let me just, this was the homogeneous solution. Now the particular solution, you can sort of look at the original ODE on the top. We can guess that the right-hand side is a bunch of constants, h, perimeter, m dot c, ts. Those are all constants. So let's guess that our particular solution is a constant. And in doing so, we get Tp is equal to Ts. So then we combine these two solutions, and then we get the combined, I guess I could just rewrite that all over. X perimeter over m dot c x times c1 plus ts. Okay. So that's our combined solution in general form. We haven't yet applied a boundary condition. So now what is our boundary condition for this problem? Let's just write the boundary condition down here. The boundary condition for this problem, go ahead, question. Yeah, well, do you know what it is? What's the boundary condition?
It should be t equals ts at x equals 0.
So think about, that's where I thought you might go with it, but actually think about where what the domain is that we're modeling. Are we modeling in the y direction, or are we modeling like the fluid as it's flowing, right? The fluid as it's flowing is kind of the thing we're trying to come up with an expression for. So the boundary condition has to be for the fluid. at its point of entrance. Right? Yeah.
Didn't we just talk about how TS is not constant? So how can we assume that the solution is constant with a TS on the right hand side?
Right. Okay, so maybe that was confusing. This thing we started off with here was for the previous example. So this is where we say q dot double prime is a constant. So I'm saying, like, I have this pipe. I've wrapped the pipe in like resistive wire, and I'm putting voltage on that. There's a constant heat flux as a function of position, right? That's a constant specified heat flux. That's one situation. Excuse me. In this situation, now we're thinking about I have like a pipe, and I'm boiling water on the outside of the pipe at a constant temperature, constant surface temperature, and it's a different situation. So with that in mind, it's a constant TS here, different solution. Good question. Okay, so the boundary condition, remember, has to be in terms of the thing we're modeling, Tm. So Tm is the thing we care about. We care about it probably at the entrance. So what would our boundary condition be in Tm? It's just going to be like the inlet temperature, right? The inlet free stream temperature. So let's call that Tm at x equals 0 is equal to T in. So the reason why like Ts is not a boundary condition is because we aren't modeling a temperature profile in the fluid in the y direction. We're modeling a temperature profile in the fluid in the x direction. Okay, so we can apply that boundary condition. In doing so, I won't bore you with the details there, but we get C1, this unknown constant, is just Tn minus Ts. Okay, so we take this thing here and plug it in there, and now we've got our full solution. Okay, so this is the approach we take to solving the problem now for specified surface temperature. What we can then do is, let's say, plot this out. So let me come down here. So let me create some plot axes, and let's just kind of sketch this out, same way we did before. So this is x, this is t. Now I've got a constant surface temperature. So let's say that this constant surface temperature is here at Ts. And my job now is to figure out what this profile looks like. Tm is a function of x. So let's say, furthermore, that the inlet temperature is T in down here. So remember I said something about this form of an exponential. So what is being multiplied by the exponential? Well, Tn minus Ts. So Tn minus Ts, or I guess Ts minus Tn in this case, where you're taking that temperature difference, and as x grows, that temperature difference is getting smaller and smaller and smaller. And eventually we converge to Ts, right? Eventually, when x is big enough, that whole first term goes away, and we converge to Ts. So you can imagine what this is going to look like, right? You start at the left, and on an exponential curve, you just sort of converge to Ts like this. So this is now my mean fluid temperature Tm. So there's two very different solutions here, right? One based on the specified surface temperature, the other based on the specified heat flux. Very different solutions. But it's good to maybe kind of anticipate that both of these are possible.